Hello and welcome to our lesson on factors and fractions. So factors are a pretty important word. We're going to see it come up over and over again. So before we turn it into an algebraic thing, let's talk about what it means to be a factor just in terms of numbers before we throw the letters in there with those numbers, okay? What does it mean for a number to be a factor of another? Well, a number is a factor if it divides evenly. So a factor is a number that divides evenly into another. So for example, if I said to list the factors of 8, 8 is a number we're all probably pretty comfortable with. So if I said tell me the factors, you could tell me that, well, 8 is divisible by 1 and 2 and 4 and 8. And those are in fact all of the factors. Now if I said what is a pair of factors, you might say 2 times 4 is a pair, or 1 times 8 is a pair that makes the 8. But technically all 4 of those are individually factors as well. Okay, now if you're talking about a number whose only factors happen to be 1 and itself, we call that a prime number. Okay, so a prime number is a number whose only factors are 1 and itself. So 8 is not a prime number because 8 is divisible by 1 and 2 and 4 and 8. So not just 1 and itself, but also these two additional factors. Okay, so if we're only divisible by 1 and itself, if the number is only divisible by 1 and itself, it is a prime number. So 1, for instance, is prime. The only things that go into 1 are 1 and itself, which is also 1. Same with 2 and 3 and 4 couldn't be on that list because 2 and 1 go in, but 5, not 6, but 7, not 8, we saw that, not 9, not 10, but 11. And then we would skip to 13, not 14, 15, 16, but 17, and 19. And this list can go on forever, but you kind of get the idea. Okay, if the only numbers that divide into your number are 1 and itself, the only factors are 1 and itself, then you have a prime number. The rest of the numbers that have factors other than 1 and themselves, we call those composite numbers because they are composed of other factors. So a composite number is a number with factors other than 1 in itself. So again, not prime is composite. So if we started our list from the beginning of natural numbers here, the smallest we'd be looking at in this group would be like 4, right? 4 is divisible by 1 and 2 and 4, or 6, or 8, 9, 10, 12, all the stuff that's missing in that other list, right? Let's see, 14, 15, 16, 18, and sometimes people confuse the words even and odd with prime and or composite, but you can have both in both groups. In the prime number group, they're mainly going to be odd numbers. There is only one prime number that is even, that happens to be 2. The rest of them are odd, but prime doesn't have to mean odd. And then composite can be either or. So we can see in our composite list that we have definitely some evens, right? All the numbers that we could cut in half, but we also have some odds in the list. And both of these lists of numbers do go on forever. So we have this endless list of prime and endless list of composite numbers, both containing evens and odds. Okay? All right, so one of the first skills we need is, other than being able to identify these numbers and know the vocab, one of the first skills we need is to be able to break down a composite number. Again, something that we will use moving forward. We would use a factor tree. Some of you have probably done this before, used a factor tree to divide a composite number into its prime factors. And your factor tree is complete when the bottom branches of the tree are all prime numbers, which would make sense. This is a factor tree to make the prime factors. And you can also use your prime factors to come up with composite factors, because composite factors happen to be products of prime factors. Okay, so let me show you all what I'm talking about here. Let's say I wanted to find both the prime and composite factors of 70. Now you could probably, or some of you may be able to look at 70 and tell me right out of the gate here what kinds of numbers would go in. So obviously 1 and itself are going to divide in, so 1 and 70. And so maybe you're thinking, okay, 1 and 70 go in, and maybe you know the rule. that if the number ends in a 0, that it's divisible by 10, or if it's even, that it's divisible by 2, or again, if it ends in a 0, that 5 goes in. So maybe you could give me some of the factors, but there are some missing from the list, and if we make a factor tree, we can actually come up with all of those factors pretty nicely. So when we make a factor tree, we want to divide this number down. Now, it doesn't matter what pair of factors you use to divide. So like I could start with 7 and 10 if those are the obvious numbers that would multiply, a pair of numbers that would multiply to make 70. Or if you're looking at this knowing that it's even and you're saying, okay, 2 is going to go in 35 times, whatever you want to do is going to be fine. So if 7 and 10 was more obvious, then I'm going to go with that. It's probably more obvious to me. So 7 times 10 does make 70. Now, 7 is a prime number, which means that's the bottom branch on that side, but 10 is composite, so we want to continue to break the 10 down. So 10 is going to continue to break down. 10 we could rewrite as a product of 2 times 5. Now, just so I'm not using the 10 in anything else that I'm doing, I crossed it off because it became 2 and 5. Okay? And then I guess I could do the same with the 70. So 70 is really made up of the prime factors 2 and 7 and 5. So from this tree, I could see my prime factors are going to be well, 1 is going to be on every list, right? So it's technically a prime factor there, but also 2, 5, and 7. Okay? Sometimes we don't put the 1 just because it's a factor of every number, but not wrong to include it. All right, now if I wanted to know the composite factors come from products of our prime factors. So for instance, if I was to multiply the prime factors 2 and 5, that makes 10, then 10 is going to be one of my composite factors. Or if I was to multiply the pair of numbers 2 and 7, I get 14. 14 is another one of my composite factors. Or if I was to multiply the pair of numbers 5 and 7, then I get 35. 35 is another one of my composite factors. Or if I was to take the whole group, multiply the 2 and the 5 and the 7, I get back to the 70, and again, every number is going to be divisible by itself. So we can get our prime factors from our factor tree, and if we take combinations of those, products of combinations of those prime factors, we will also arrive at our composite factors. Okay? So there they are. There's that. Now, what if I asked you a question like this one? It says to find the prime factorization of 60. This is basically going to involve the factor tree again. So the prime factorization, that is another way to say list out the prime factors. Okay, so you can kind of see the prime factor in the prime factorization there. So let's use a factor tree. 60, again, we could say is 6 times 10. Now these are both composite, so I would continue to break down both branches. So 6 we could say is 2 times 3, and 10 we could say is 2 times 5. So all of those prime numbers at the bottoms of those branches, those make up what we call the prime factorization. So we would say the prime factorization here is, we could say 2 times 3 times 2 times 5, or you may see this condensed because you have two 2's in there. 2 times a 2, we could shorten that and say that's 2 squared. And so you could also see this written as 2 squared times 3 times 5, but either one is acceptable. Okay, so that is the prime factorization. That's a list of the prime factors that make your number. Now, if I said list all the factors, we're really doing the same thing we did in problem 1, where we found the prime and the composite. Those two lists together would make all of the factors. So let's go ahead and break down the 150. It's good practice again. Let's see, this could be 10 and 15, and then 10 could be 2 times 5, and then 15 is 3 times 5. So if I said what are the prime factors, Not the prime factorization, where I have to list all of them, but just what are the prime factors? Well, 2 goes in, and 3 goes in, and 5 goes in. Now, I know there are 2 5s in there, and I would definitely need those if we were looking for the prime factorization, but here we're just listing out the factors, and it's not necessary to list them twice. So those are my prime factors, and I went ahead and threw 1 in the list. Now, if I want my composite factors, then I need to look at combinations of these prime factors, okay? So combinations like, again, 2 times 3 would be 6. Oops, I forgot my writing over here. Let's say composite factors. 2 times 3 was 6. I'm going to add that to my list. Or 2 times 5 is 10. I'm going to add that to my list. Or we've got 3 times 5, which makes 15. I can add that to my list. Or the whole combination. Let's see. The whole combination, another color here, 2 times 3 times 5, that's going to be 30. I can add that to my list. Now, I didn't put the second 5 in the list, but in order to come up with the composite factors, I'm going to probably have to do that, because if I multiply, for instance, the 5 and the 5, I get 25 as another composite factor. Or the 2 and the 5 would be 50 as another composite factor. Or the 3 and the 5, which would be 75 as another composite factor. So that extra factor of 5 helps me get that extra list, okay, with those combinations. And I think I've gotten them all. So if I said list all of the factors, so all factors, we're just going to consolidate our lists here. So we've got 1, 2, 3, and then we're going to go 5, 6, 10, 15, 25, 30, 50, 75, and then let's not forget the number itself, which is 150, and that really should have been on this list as well. Okay, so there it is. Now, I probably wouldn't ask you to do anything as crazy as 150. I mean, I could, and really, if you didn't want to do the factor tree, you could just take 150 with the calculator and say, divide by 1, divide by 2, divide by 3, and figure out what are all the numbers that divide in, although that could take a while. If you saw this in an assignment, it'd probably more likely be a more manageable number like 70, okay? But the process is there nonetheless, so you should be able to handle that, okay? Although if you find yourself struggling, feel free to reach out for some extra help. All right, so let's continue on here. What are we looking at this for? What does this have to do with where we're going? The reason we want to have an understanding of how a number breaks down and what its factors are is because it plays into how we handle fractions. Now, I'm sure we know what a fraction is. No, it's not just another math F word. A fraction is really a division problem. So this fraction bar is really just division. But we tend to be a little phobic about fractions, okay? Let's just get some vocab straight first. So the top of the fraction, we call that the numerator of the fraction. The fraction bar itself, right, we call that the fraction bar. That fraction bar is also the same as division. So when I'm reading that fraction of a over b, I could also say it's a divided by b. And then the bottom of the fraction is called the denominator of the fraction. Okay, so the numerator, that's the top, and the denominator, that's the bottom. All right, and one little stipulation with fractions. Not sure if you know, or maybe you have forgotten, but there is one specific number that we cannot have in the denominator, in the bottom of the fraction, and that number happens to be 0. Think about if you had 0 in the bottom of the fraction, like 1 over 0. Okay, when you give a fraction like 1 over 2, that's one of 2 parts. So you had half of the pizza, you had 1 of 2 slices, or something like that. What would this mean here? You have 1 of no slices? Can you have 1 part of nothing? Nope. And for that reason, and many others, which could be a whole side lesson, 0 in the denominator of the fraction is undefined, so the denominator cannot equal 0. The denominator cannot equal 0. 0 in the bottom of the fraction, and the denominator of the fraction we say is undefined. Okay? Now, what we got to be able to do are the basic things with fractions. We should be able to reduce or simplify, same kind of word there. We should be able to perform our basic operations, which would be add, subtract, multiply, and divide. And the factor concept that we just looked at will help us in this reducing. So if you're comfortable reducing fractions, this might not be necessary for you, but for people that are uncomfortable, or maybe you just never had a good foundation with it, you're going to reduce, or you're able to reduce fractions because, or if, the numerators and denominators have common factors, okay? If the numerator and denominator of a fraction have any common factors, that means if you were to break them down using a factor tree and list out the prime factorization of the numerator and the prime factorization of the denominator, then those common factors can be reduced out of our fraction. They can be reduced out. So for example, let's say we broke down the 6 that's in the numerator here. 6 we know is 2 times 3. That would be the prime factorization there. Or if we broke down the 8, 8 would be 2 times 4. And then 4 we could break down as 2 times 2. So if I rewrote my fraction, I could say that 6 over 8 is equal to... Oh man, I should have organized this a little differently. I'm sorry. We could say that 6 on the top of the fraction is 2 times 3. And we could say that 8 on the bottom of the fraction is 2 times 2 times 2. And if there is a common factor, again, that common factor can be reduced out. So the common factor of 2 can be reduced out, and once we've reduced all of our common factors, what we have left is our simplified fraction. So in this case, we have 3 left in the top, and then we have 2 times 2 in the bottom, which is 4. So 3/4 is the simplified version of that fraction. Now, I'm sure many of you can look at 6/8 and know that it reduces to 3/4, but this is the how and the why, in case you get stuck on something later, okay? That is the how and the why of reducing fractions. So let's try that again, and let me try to color code this a little better. So let me break down the 15. 15 becomes, did I do that over here? Yeah, 15 becomes 3 times 5, and those are prime, so we can end that one. And then 45 is, let's see, 5 goes in 9 times, and then 9 is composite. It's made of 3 times 3. So if I was to rewrite this fraction, on the top, the 15 can be rewritten as 3 times 5. On the bottom, 45 can be rewritten as 3 times 3 times 5. Those would be the prime factorizations for those numbers. So what do we have in common? Well, 3, a pair of 3s that can go there, and then some 5s can reduce out as well. And what is left becomes our simplified fraction. So on the bottom, clearly we have left a 3. Technically, what's left on the top? Well, remember I said in the beginning, right? Technically, our prime factorization includes 1. We just don't tend to see it. We kind of assume that it's there, or it's implied that it's there. So there is technically still a 1 in the top of that fraction. And so 15 over 45 reduces to 1/3. Now again, if you can look at 15 over 45 and say, hey, I know both of these numbers divide by 5. 5 goes into 15 3 times, and then 5 goes into 45 9 times, and then reduce that again. 3 goes in there once and in there 3 times. I am totally fine with that. Or maybe you notice up front they're both divisible by 15. That's all good. This is really just a process to help you if you struggle with it, or again, this is going to build into algebra later, so these skills are still helpful to have. All right, so that's how we can reduce or simplify fractions the long way. What about multiplying? How do we multiply fractions? For instance, if I said to multiply 1/5 times 3/4, hopefully we remember that when we multiply fractions, we multiply straight across the numerators, straight across the denominators, and then once we're left with one fraction, we'll reduce that if we can. Okay, so for example here, straight across the top, 1 times 3 would be 3. Straight across the bottom, 5 times 4 would be 20. And 3 and 20 have nothing in common. I can't break down the 3. If I broke down the 20, 4 times 5 and 2 times 2, nothing's going to be in common there. So since that has no common factors, that's going to be our simplified answer, our simplified product, okay? Now here, when I multiply straight across the top, 6 times 1 makes 6. When I multiply straight across the bottom, 7 times 3 makes 21. Here we do have some common factors. So 6, again, if I broke 6 down, that's 2 times 3, so 2 times 3 on the top. And 21, if I broke that down, 21 is 3 times 7, so 3 times 7 on the bottom. We've got a common factor of 3, so those can be reduced out. So this simplified fraction becomes 2 over 7. So we multiply straight across and then we can reduce. Now again, if you're comfortable with fractions and you noticed here that you could reduce, I'm totally fine with that. By all means, if you know the rules, use them. So 3 would go in here once and in here twice, and then multiplying straight across we get 2, and multiplying straight across we get 7. Same answer, but if you're not so comfortable, feel free to do some of these things the long way. Okay? Up to you and your comfort level. Alright, so that's multiplying. If we can multiply fractions, we really should be able to divide because we don't actually divide fractions. The rule for division is we don't divide fractions, we multiply by the reciprocal. So for fractions in division, we don't actually divide fractions, we multiply by the reciprocal. What does that mean? That means that we keep our first fraction the same, but we're going to change our division to a multiplication problem, and we're allowed to do that as long as we flip the second fraction. So reciprocal means we want to flip. The top becomes the bottom becomes the top. Okay? And I know you're probably like, why? There's a good explanation for it. It's just I could drag this on, and I don't want to punish you with all that unnecessary explanation. If you want a side story on it and to know why we end up multiplying by the reciprocal, feel free to reach out, and I'd be happy to give you that mini lesson. But this is just a review for us here. So multiply by the reciprocal, that is the rule for dividing fractions. So again, we're keeping the first fraction the same, changing our division problem to a multiplication problem, flipping the second fraction, and then once we have a multiplication problem, just like we did a second ago, we multiply straight across the top and reduce if we can. Okay, so for instance, when we see 2/3 divided by 1/4, that is really 2/3 being multiplied by 4 over 1. So keep this the same, right? This stayed. And then we change the division here to multiplication. And then we flip the second fraction. So 1 over 4 became 4 over 1. So we are keeping and changing and flipping. Again, this is all going to come back into algebra. So it's great review. So now we have a multiply problem. Multiplying straight across the top. 2 times 4 is 8. Straight across the bottom. 3 times 1 is 3. No common factors there, which means that's going to be our simplified quotient. That's what we call the division there. And then here, same thing. We are going to keep the first fraction, a half. We're going to change the division to multiplication. We're going to flip that second fraction so it becomes 5/3. Multiply straight across the top to make 5, straight across the bottom to make 6. Nothing in common with 5 and 6, and that's going to be our simplified form. Okay, so multiplying, dividing, not so bad because it doesn't require anything fancy like a common denominator. That's what we have to have if we are adding and subtracting. So fractions have to have common denominators. We need to have the same denominator in order to add or subtract. And a common denominator has to be a common multiple of our denominators. And once we have a common denominator, we'll be in good shape. We would keep that common denominator. We would go ahead and combine our numerators and go from there, but we've got to have a common denominator first. So if we do, this is a simple problem. If I have 3/5, if I have 3/7 and I want to add 2/7, then altogether I have 5/7. Okay, so think about this like a piece of a whole pizza with 7 slices. If you had 3 of them here and you had 2 of them there, that means you have 5 of those 7 slices altogether. So when we're adding, we need a common denominator. If we have it, we keep that common denominator. We're just combining what we have in our numerators. So 5/7, and that can't be simplified, so it's 5/7. Okay? Same thing here. We've got a common denominator, so we would keep it, and then we're going to combine our numerators. This time we're combining with subtraction. So 5 minus the 1 makes 4. No common factors. That's going to be our answer. It's not so bad. unless we don't have common denominators. So if we have a problem like 5 over 12 and we want to subtract 1 over 6, that can't happen unless we have common denominators. So to establish a common denominator, we need a common multiple for the denominators. So for example, multiples of 6, well, 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18. That would be a list of multiples, right? If I was listing out multiples of 12, 12 times 1 is 12, 12 times 2 is 24, 12 times 3 is 36. Those would be my multiples there. What I need is a multiple they have in common, like 12. And if it's the smallest multiple they have in common, it is the least common denominator, and that's what we want to use in our problem. So our least common multiple for 6 and 12 happens to be 12, which means our goal is to get both of these denominators to be 12. So the first fraction is great. It already has a denominator of 12. The second fraction doesn't. So we're going to have to manipulate this second fraction here. So I know to make the 6 that I have here a 12, I'd have to multiply by 2. 6 times 2 would make that a 12 there. But in order to not change the value of my fraction, I have to do the same thing on the top. Because if I multiply by 2 over 2, what is 2 divided by 2? Well, that's 1. And when you multiply something by 1, you're not changing its value. And so I want to clean this up because I've made a mess everywhere. Multiply my second fraction by 2 over 2. So now I'm looking at 5/12 didn't change, and the minus didn't change. But now here, I have 1 times 2, which is 2, and I have 6 times 2, which is 12. So instead of reducing out the common factor, we're putting a common factor back in. So like the reverse of what we're just doing. So now I can actually put these together. We've got common denominators, so we keep the common denominator, and we combine our numerators. This time, again, combining with subtraction. So 5 minus the 2 leaves me 3. Now these two have something in common, because if I was to break down 12, 12 is 2 times 6, and 6 is 2 times 3. And so really what we're looking at here is 3 over 2 times 3 times 3. I'm sorry, 2 times 2 times 3, and that means we've got a 3 in common. So if that 3 cancels out, reduces out, what do we have left? Well, in our denominator, 2 times 2 is definitely 4, and again, there's that implied, that invisible prime factor of 1 that's still up there, and so 1/4 is going to be our simplified answer. Okay? Are you having fun yet? I hope so. Alright, how about this guy? So 3/8 and 7/10. We need a common multiple for 8 and 10. So what I like to do is start with my bigger number like 10, and just start listing out the multiples until I find one that I know 8 goes into. So 10 times 1, or 2, or 3, or 4, and then I would stop, right? That number is divisible by 8. So if I made my list of multiples of 8, then that's going to be the first one that those two lists have in common. So 40 is going to be my common multiple. That's the goal then, to make these both have a denominator of 40. So this fraction, if I multiply 10 by 4, I'll get to 40. But I got to do the same thing on the top. And this one, if I multiply 8 by 5, I'll get 40, and I got to do the same thing on the top. So I'm looking at 15 over 40, right? Plus, now I have 28 over 40. And now I can put these fractions together. So I can keep my common denominator, and if I combine those numerators, 15 plus 28. Let's see, what is 15 plus 28? That's 3, I carry the 1, that's 43. So 43 over 40, and 43 is a prime number, which means we're not going to be able to break that down or find any common factors. So 43 over 40 is our simplified fraction. Now, that's an improper fraction. That's what we call it when the numerator is bigger than the denominator. But improper fractions are totally fine. In fact, if you had any inclination to make that a mixed number, we don't really do much with mixed numbers in algebra. So the improper fractions are preferred over mixed numbers. Okay, so no need to change that to a mixed number. All right, I think that, yep, that's it, guys. So hopefully you got a good little refresher on how to reduce, add, subtract, multiply, divide fractions, and how to make factor trees. But if you, again, need some extra help, then feel free to reach out. You've got some practice problems to work on. So again, if you're struggling or you need me, then an email or a text away. All right, until next time, take care.